Good afternoon, everyone, and welcome back to Spark Summit Europe 2015. You are in the developer track, and I am super excited to introduce our next speaker. He is a software engineer at Databricks and one of my team members, so I'm very happy to be able to work with him. Please, everyone, welcome Andrew.
Thank you. Hello? Hi, can you hear me? All right. Hello, everyone. My name is Andrew, and I'm super excited to be here. The title of my talk today is SparkUI Visualization. So I am a committer of Spark, and I work at this company called Databricks. We do something like this. You've already seen this in yesterday's keynote, but basically you can start worrying about cluster management and all the complexities in using Spark and produce pretty graphs that look like this. At Databricks, I've worked on several features in Spark. The last one, dynamic allocation, I've given a talk on that in the past, and today I'm going to talk about the DAG visualization. Maybe sometime in the future I'll talk about unified memory management. So this talk might be a little different from the other talks that you've seen so far in this conference, in that it will be mostly demo-driven, so fingers crossed. And I will be showing you graphs that look like this, and some more graphs, and some more graphs, and some timelines, some cats, some charts. So the purpose of the demo is to walk through how to debug your application through the SparkUI. In particular, I would like to showcase the visualizations that were added recently and show how they add value to this process. So before I begin, I'd like to share a quote. Most of us listen to music to understand how beautiful it is. But often how we present statistics is that we just show the notes. We don't play the music. So this is spoken by Hans Rosling, who is a professor of public health in Sweden. He looks something like this. He's done a lot of work on data visualization. He's shown up on Tech Talks and stuff. And he's used data visualization to try to extract social trends. So essentially what he's trying to say is that a lot of people look at data and they get lost in the details. So they get lost in the low-level numbers, the tables and like percentiles and so on. But they fail to appreciate the bigger picture of what the data is trying to say. So as an example of that, here's some data from Trulia, which is a real estate company in the US. So they've released some public data on how users use their website to search for houses. So here you can see, for example, there are a lot of searches in San Francisco. It's a pretty popular city. About like 40% of the people use mobile, something like that. But you can't really make any confident assertions on what the data is trying to point at. So instead, a better way to represent this data would be through visualizations. So what you see right here is essentially a heat map of when people use their website. So you can see at a glance that at around 8 or 9 p.m., that's when people start picking up. And also on Sundays, that's another busy time. What's somewhat surprising is that people go onto the website much more frequently on Sundays than on Saturdays, presumably because they think they still have another day to look for the housing, so that's a good reason to procrastinate. So at a glance, you can quickly tell several insights from this, but more importantly, you can share these insights more easily to other people. So it turns out that Spark also produces a lot of data. So each Spark application has a bunch of events. So for example, a task end event, stage completed, or like executor loss, etc. So each application optionally logs these events to a file called event log, which looks something like this. It's stored in JSON format. And each line right here represents one of those events. So this is useful because it tells you something like how many bytes a particular task built to disk, how long a stage took to finish, and so on. So as in the Trulia case, a better way to represent this data is to visualize it. So now no longer do you have to read over the sheet music painstakingly note by note. Instead, you can just play the music. Oh, well. OK. OK, cool. So I'd like to showcase how to interpret these visualizations through a demo. In particular, I'll be doing movie recommendations using Spark's machine learning library, MLlib, analyzing Wikipedia dataset using data frames, and finally running word count using Spark Streaming. So to do this, I prepared several notebooks and data bricks. The first one will do movie recommendation using the alternating least squares algorithm built into Spark. So because it takes a while to run, let me go ahead and just run all, and then in the process, in the meantime, I'll explain what it's trying to do. So the high-level goal is to find users that like comedy movies and recommend movies for them. OK, so there's several high-level steps. The first is that we have to find users that like comedy. And for that, I have two criteria. The first is all the 5 stars given by the user have to be for comedy movies. The second one is that the user has to have given at least 10 5 stars. So that's a pretty good indication of whether someone likes comedies or not. And then we'll train the model, and lastly, use that model to recommend movies to one of these users. So it looks like it already finished. Let's scroll down to see what the recommendations are. So I actually haven't seen most of these movies, but the one that I do know is Airplane, and that's a hilarious movie. So at least we have one comedy in the recommendations. I think this one is also a comedy, but I'm not sure. So this model kind of works. Can't really verify that, unfortunately. But let's go back to look at where we trained the model. So I've collapsed the cell, and now I will expand it to show you the contents. So using Spark's machine learning library, this is fairly easy to do. All you need to do is call als.train on your ratings RDD. This one line ran 6 jobs, and I can expand this to look at the jobs that it ran. So now let me go to the Spark UI for this particular job. So this is the So this is the jobs page on the Spark UI. By default, the DAG visualization is not turned on, so it looks something like this. And then if you expand it, you end up with a graph that looks something like this. So the way to read this is as follows. So each of these dots right here, these are RDDs, right? So if you hover over them, you can see the name of the RDD if they're not named, right? The green ones here are just cached RDDs, right? So this one in particular, you can see it's called rating blocks, and that's because we explicitly gave a name to this RDD. Okay, and then each RDD in turn is grouped by the operation that created them. So here, somewhere in the code, we did a text file, and then this would show up on the UI. And then further, each one of the operations are grouped in the stage in which they are run. Okay, so the last point actually highlights an optimization in Spark where we pipeline operations. So in Spark, we try to avoid shuffles where possible. So shuffle is like an all-to-all communication across all the nodes. It is usually pretty expensive because it involves a lot of network, disk, and I/O. However, if the partitioning doesn't change, then we don't actually have to do a shuffle. And in Spark, we never actually start a stage unless we have to do a shuffle. So as an example, here we have a map followed by a map and a map partitions in the first stage. All of these are pipelined into a single stage. So note that this optimization is not possible if not for Spark's another optimization, which is lazy execution, right? So imagine for a second if I had run this map right here, if I run that eagerly, then I wouldn't be able to pipeline my operations like this. Okay, so let's go ahead and look at the next job. So this looks pretty similar to what we saw before, with one notable exception, which is that the first stage right here, the first stage is skipped. And that's pretty much exactly what the name suggests. So this stage is not run in this current job. And in Spark, there's an optimization where if the shuffle files for this for a shuffled RDD, this one is a shuffled RDD, has already been computed in the past, then we simply reuse that shuffle. We reuse those shuffle files. So this is very important for iterative applications like ALS. Okay. So the next stage, the next job, however, is where all the real magic happens. So the first thing you'll notice is that the first 4 stages are skipped, and this entire job is actually much more massive than the rest. So starting at stage 17, it starts looking pretty similar, right? So almost all of the stages look identical, right? So in fact, what's actually happening is that they're not totally identical. In ALS, each iteration spans 2 stages. So stage 17 and stage 18 actually belong to 1 iteration. Here, I happen to be running 10 iterations, right? So we should expect 20 such stages. So stage 17 essentially computes the user factors, while stage 18 computes the item factors, right? And we keep doing that, and therefore it's alternating. Okay. So I'm not going to go into the detail of this algorithm any further, but my high-level point is that with the DAG visualization, you can see several Spark's optimizations. So normally for small applications like word count, it's probably reasonable enough to just look at the code and understand what it's doing. But if you're building something complicated on top of Spark like ALS, then it's actually fairly difficult to make sure that you actually take advantage of many of Spark's internal optimizations as much as possible. And having a DAG visualization like this really helps you understand what your application is doing. OK. So now I'll move on to the second example that I prepared. So as before, let me just go ahead and do a run all. All right. So in this example, what we want to do is analyze a Wikipedia clickstream data. So this data set tells us how many users visited what articles, how many times, and where did those users come from. Okay. So in a little more detail, each row in this Wikipedia article, you can think of it as a source-destination pair. So it represents essentially like a link in the Wikipedia article and where the link came from. Okay? So cur title is the destination, and prev title is the source. Right? And the source can come from other sources like Google or another Wikipedia article. And then n is the number of times the link was followed. So you can think of this as the weight of the edge, if you imagine this whole thing as a graph. Okay? And this only describes visits in February. So with this data set, we can answer questions like the following. Which articles were the most popular this month? Let me actually zoom in a little bit. Okay. So the first thing you'll notice is that 87th Academy Awards was probably happening around that time. 50 Shades of Grey, I think the film was released around that time. And then I think what's the most striking is that it's only February, but people are already looking at the deaths in 2015. So that's pretty grim. OK, so now let's go ahead and answer a slightly more complicated question. So the question is, what pages multiply input clicks the most? And by this, I mean what pages brought most traffic to other pages in Wikipedia. So to find that, there are 3 steps. First, find the number of input clicks for an article, and then find the number of output clicks for the article, and then divide it to find the multiplication factor. Right? So to do this in data frames, all I need to do is create two data frames right here, and then join them together. Right? So you notice that the join expression right here uses a UDF, so a user-defined function, and it's pretty silly. All it does is compares the lowercase forms of the 2 titles. Okay? So looks like it's been running for a while. So let's go ahead and see what's going on. So the first 2 stages are already completed, but the last stage is still running. And it looks like it hasn't even completed any tasks so far, so something is fishy. OK, so I'm going to click this I right here to go into the stage page. OK, well, from all these like tables and text, you can't really see much about what's going on. So for data frame jobs, there's actually something special called the SQL tab. I'm not sure if you can see it. It's right here. Okay, so this SQL tab contains information that's specific to your queries. So instead of showing you things on a low-level basis like jobs and stages, it shows you the higher-level constructs like physical operators. So let's click into this query that I've been running. And what we'll see here is a query plan. Right? So on a high level, it looks something like this. Now let's walk through it a little bit. So the in-memory, so first we start with a table scan, and then we do a filter. So this filter is actually pretty good, right? Like the reduction factor is about 50%. So it's good to have it. And then we do a project. We do this aggregate right here. So this is just partial aggregation. Don't worry about the details about what it's trying to do. And then we do a shuffle, right? And then we do a final redo side aggregation. Okay, so we do all of that. And we do like roughly the same thing on the right. And notice that we end up with a Cartesian product. So for those of you in Aaron's talk yesterday about the production use cases in Spark, you remember that he warned against using Cartesian product. And for a very good reason, because Cartesian product is very expensive. Essentially what it's doing is joining every single row on the left with every single row on the right. And it takes forever. And you can see the number of right rows is like kind of crazy. All right, so we found the problem. And let's see which part of the code triggered the Cartesian product. So first, let's stop this. OK. Let's see. Well, looks like the problem is in this UDF, right? So when we do a join right here, we're just passing in an arbitrary function. So by definition, the user can do whatever they want in this function, right? However, if you look at the body of the UDF, what they're really doing is just a simple equality check. So because they're using an arbitrary user-defined function, they can't. So the SQL query optimizer doesn't know how to optimize this join because it doesn't understand it, right? So that's probably the problem. OK, so let's try a better UDF. So here in this case, I'm explicitly using the built-in Spark SQL equality expression that the underlying query optimizer does understand. So let's go ahead and try to run this. Note that I'm still using UDFs here to convert the title to lowercase. Okay, I'm just not using it to do the equality. So hopefully this should finish much more quickly. Right. Ta-da! Okay, and then we can look at the Spark UI again to confirm that we're no longer using the Cartesian product. So as before, I'm going to go to this SQL tab. I'm going to go to the most recent query that I just ran. And so as expected, we're using sort merge join instead of Cartesian product. Okay, so that's why I complete it much more quickly. So another thing I wanted to showcase with this notebook is the event timeline. So I'm just going to go ahead and click into one of these stages, right? And then click this event timeline here. So the way to interpret this is each one of these bars represents a single task. And the longer the bar is, the longer the task actually took to run. Further, each task is broken down into different colors to represent what the task is doing at a given amount of time. So for the most part, this looks all right. It looks like this particular executor has many tasks scheduled to it. And then if we scroll down, we can see the task allocation for other executors for this stage. So it looks like it's pretty evenly distributed. So one thing to point out here is that it looks like this particular task, it has like a lot of blue stuff in front of it. If you look at the legend, this means scheduler delay. Not exactly sure how that one particular task has like more scheduler delay than others, but that's probably not that big of a deal. Another thing to notice is that each task seems to have like a lot of yellow stuff at the end. So this corresponds to shuffle write time, meaning these tasks are spending time to write the shuffle files for next stages to consume. So this stage is a shuffle map stage, in other words. OK, so that's the event timeline. Let's move on to the third application. So in this notebook, I'm trying to run word count on a stream of words. Okay, the input data from that we're going to consume is actually generated by this notebook itself for simplicity. In particular, I'll be drawing words from the Act of Abjuration in 1581, which is when Netherlands gained independence from the Spanish kingdom. So this is a monumental moment in Dutch history, and so I'm going to do this. So let's run this notebook. So on a high level, what we're going to do is, well, essentially just run the word count. But let's look at this in a little more detail. So the first thing you'll notice is that the batch interval is 2 seconds. And then every 2 seconds, we also pump 50 words into the stream. Okay, that's just like the data generation. And then we do some word count here. And then we populate the table every batch. And then we merge the old counts with the new ones. Okay, so essentially we end up with aggregated word counts. And so here you'll notice that we've seen the word kings 3 times, hatred 2 times, okay, something like that. And because this is a live stream of, this is running a live application under the hood, if I run this again, I'm going to get updated counts. So now you notice that Prince is like being, we saw Prince 8 times. Okay, so the thing that I wanted to showcase in this example is the streaming tab. So just like SQL, streaming also has a tab over here, right? Okay, so I'm going to click into this. And this tab shows you a lot of streaming specific information. So for someone who doesn't use streaming, this may not like make a lot of sense. But I'm going to walk through each one of these graphs one by one. So the first one, this one right here, is the input rate. So it's pretty straightforward. It's the rate at which input data comes in. So because we're generating data in this notebook, it's totally static, and there's not much exciting going on here. So the histogram here, the histogram here is a little hard to understand at first. So all you need to do is tilt your head sideways like that, and then it'll start making sense to you. Okay, so the next thing I want to talk about is the scheduler delay, this one. So in any streaming applications in general, if the rate at which the input data comes in is faster than the rate at which you can process them, then what ends up happening is you're going to have to put some jobs in the scheduler queue. And the time for which the job stays in the queue is known as the scheduling delay, right? So in general, we want the scheduling delay to be as low as possible. Certainly, we don't want it to be growing like this, right? So this is actually potentially concerning. This represents a streaming system that is not, a streaming application that is not stable. All right, let's come back to that. So the next thing is processing time. This is the time spent actually running the underlying Spark jobs. So one thing you'll notice is that, remember before I mentioned that our batch time is 2 seconds. However, the processing time took more than 4 seconds. So this is definitely alarming. And then the other thing to note is that there's a stable line right here, and all of our batches are above this stable line. So this is why the system is not stable. And then the last one is a little more straightforward. It's just the sum of the 2 delays above. Okay, so let's try to find out why it's growing like this, right? Let's try to find out why the processing time is so long. So to do that, you can hover over this graph right here, and then click into one of these batches. Okay, so I clicked into a batch, highlights the batch in the batch table. I'm going to click into the batch again. So here's the batch page. Okay, and then so each batch can run multiple jobs. In this case, it only runs one. So I'm going to click this to go into the job page. So this is what we're familiar with. This is just the job page that you've already seen before. In this job, looks like there are 2 stages, one of which is much longer. And the one that's longer is for each RDD. So I'm just going to click into this. OK, so now we're on the stage page. And if you look at the event timeline, you'll immediately notice something suspicious. So my cluster has 4 executors, and each executor can run 4 things in parallel. However, from this, it looks like this stage is running exactly 1 task, right? So we know somewhere in the code we must have had set the number of partitions equal to 1. And this is really slow because this whole thing, it takes like 6 seconds. And we could have completed it much sooner if we had broken it down into many tasks. OK? So now let's go back to the notebook and to try to figure out where the issue is. OK, so here we're doing word count. Ah, what is this? So it looks like here we're only setting the number of partitions to 1. So to change that, let's set it to 100. So how did I pick 100? Well, so I know there are 16 CPU slots in my cluster because I have 4 executors. Each of them have 4 cores, right? So usually we recommend using several multiples of the number of slots in your cluster, so you have several waves of execution to mitigate stragglers. So I'm just going to set it to 100 here. And let's try again. So I'm going to try it again on a new cluster, just so we don't have like leftover state from the SparkUI. So now let's go ahead and run again. OK, so what do we expect to happen here? Well, we increased the number of partitions in the reduce task. So there's more parallelism there, and so the processing time should be much slower. And if the processing time is much lower, we should expect the scheduling delay to no longer increase as we previously saw it. So now let's verify whether that is the case. OK, so we end up with some word counts. That's good. Let's look at the SparkUI. I'm not sure that's OK. Let's look at the SparkUI. Go to the streaming tab. And as expected, the scheduling delay is now flat at 0. So this is an example of a stable streaming application. So all I did, by the way, was to change that one number from like 1 to 100. But without this kind of UI, it might be hard to ever find that out, right? Processing time, you'll notice that it now kind of fluctuates a little bit. But that's OK, because the average is still comfortably under 2 seconds. OK. So that marks the end of the last demo that I wanted to show you. Let's recap on some of the things that we saw. So the first thing that we saw is the DAG visualization. Looks something like this. And this showcased a lot of Spark optimizations. So for users developing complicated applications on top of Spark, this is pretty useful in seeing whether you're doing the right thing. The second is to avoid Cartesian product. Just always try to avoid Cartesian product. And the way to do it is to just use the inbuilt SQL equality expression instead of doing the equality check in your UDF. Okay. Third, we saw that scheduling delay should not increase like this. So this is an example, once again, of an unstable streaming application. And you can use the UI to diagnose that. Lastly, the parallelism should be at least the number of slots. Otherwise, it doesn't make sense. Like, why are you running Spark on a cluster when you're not taking advantage of the parallelism? So in fact, as I mentioned before, we usually recommend several multiples of this. So you can take advantage of the straggler mitigation in Spark. Thank you very much.
Any questions? Awesome. Thank you, Andrew. Give him a big hand.